but this work is a joint work of Fudan universities with Drexel universities and Oregon State universities. And Professor Yuan Hongtai here is our important collaborator for this work. Okay, I'm going to introduce our work on architectural refactoring. And in these 2 days, we will talk so much about the technical depths. So when the technical depths are very heavy, the solution is going to say that we're going to do a refactoring, right? And refactoring in an architectural way. The architectural refactoring actually includes decoupling the big modules into small modules, retrofitting the code into design pattern, etc. However, if you want to do an architectural refactoring, we have to do 2 things. The first thing is that we need an idea design in our mind. That is a target. And the second, we need a solution consisting of a sequence of refactoring steps towards the project. That is the solution. And an industry study is conducted by Tokuda and Battery, and this shows that their architectural refactorings consisting of over 800 low-level refactoring steps, which means that if you want to do an architectural refactoring manually, it is very challenging. The reason lies in that when we are refactoring towards our idea designs, each time we're doing that, we have a lot of refactoring choices. If we made it wrong, we may never get to the end. And existing approach actually are proposed to fully automate an architectural refactoring. And they are aimed to optimize some software design metrics by recommending a sequence of refactoring steps. But however, the problem lies in 2 folds. The first one is that the matrix can hardly represent the design in the mind, just like Mathias and the statistical the matrix is very hard to really represent what the design we need. And the second is that the users can never in control. And this approach recommends a sequence of refactoring steps. The user cannot control in the process of applying this large number of refactoring steps. Therefore, they do not have confidence in the final refactoring results. Thus, they will not use it. In our work, we propose an approach called refactoring navigators. It is a metaphor of vehicle navigators. Just like the traditional navigators, given the map and given the source and the destinations, the navigator recommends a path from the source to destinations. In addition, during the navigations, the drivers or the users can provide their feedback going left, going right, so that the navigators will recalculate the path towards their destinations. In our refactoring navigators, yes please.
Yeah, can I ask a question on that one? Just picking up on the metaphor. When you've got the set map, you know where the target is.
Yes.
But when you're building a system with
yes, that's what I was going to introduce just like this.
You don't know where the target is.
Exactly, but not yes, but no. I'm going to introduce later. In our refactoring navigators, the source is our current code implementations, and the destination. And your question, your destinations is a user-specified intended design. That is, we ask the user to provide their design, to draw their designs. And we will recommend a sequence of refactoring steps. And the user can either reject it or accept it.
How do they know where that particular target is?
Well, actually, when you are doing refactoring, when you do an architecture refactorings, we have a design, have an intended design in our mind. That is our assumptions. When we do the architecture refactorings, we must have an intended design in mind. Otherwise, how do we decide what to do refactoring? We have a goal. We must have a goal, right?
Yeah.
Otherwise, why would we do refactoring? Well, if we do not know the design, why do we refactoring?
Well, yeah, but in a feature-driven approach, when you're doing test-driven, you do the unit tests first, and then you refactor.
Even that, we do have a design, have a target.
Well, the target is to pass the tests and then look at the smells.
Yes.
Based on the smells, you do the refactoring then, don't you?
Yes. Well, I'm going to
I comment on that. So I think we are talking about 2 kinds of refactoring targets here. I think what Lane was targeting at, like refactoring, like we see, like we apply a pattern that doesn't exist before, And we do want to decouple the two big modules by applying some pattern, inserting some design rule. And that's kind of refactoring, I think have in mind. And low-level refactoring, like change the parameter name, I think that's not within the scope of this work at this point.
Let me go through later. Okay. So let's assume that the developers will have a design. Usually in architecture refactorings, we want to do an architectural way. It is involve a lot of work. Actually, we need a design. And based on the user-specified intended design, and our refactoring navigator is going to recommend a refactoring path, which consists in a sequence of refactoring steps. Each steps, the developer can either accept it or reject it. And based on their acceptance and rejections, we will going to take their feedback and to improve their further recommended results. By this means, we give the control back to the users. First, we do not use a single matrix. We let the developers to provide their targeted design, so they have such a flexibility. And second, and more importantly, and we will use the human feedback to further improve the recommendation. Now let me give a simple example to show how our refactoring navigators work. And then motivated cancel is the bus monitor system. And the main feature are receiving the dynamic bus informations, and it also shows the operation informations on the GUI. And also, more importantly, we need to update the bus operational information on different views. The current implementation is like this, and the bus monitor class interacts with 3 different curve views, and such implementations will have 2 design problems. The first is that it is not convenient to the extensions because the bus monitor interacts a lot with different views. When we want to extend a new view, we have to incur a lot of modifications on bus monitor. And the second, the bus monitor is a God class. It is responsible for too much. It is responsible for the GUI code. It also responsible for the code of business logics of bus information. Therefore, an ideal design is like this. So we first need to separate the business logic of bus information from the GUI code, from the GUI module. In addition, we need to abstract an abstract view from a concrete view, so that an extension of a new view will not incur too much change on the GUI modules and on the bus monitor modules. To this end, the GUI modules can only allow to create a concrete view, but other dependencies are not allowed. In our refactoring navigators, the source is our implementation, and the destination is our design. We're going to recommend a refactoring path consisting low-level refactoring steps towards the design. And in addition, when the user is given a feedback on certain steps of the refactoring path, and the refactoring navigators will recalculate the refactoring path towards the destination. Okay, let me show how the refactoring navigator do this. First, the refactoring navigators, we're going to generate a refactoring model represents the difference between the source and the target. And in such a refactoring model, we can see that the design has 4 missing dependencies. In addition, it has an unexpected dependencies from the GUI module to concrete modules. Based on such a refactoring modules, and the refactoring navigators going to recommend a refactoring solution. And the first step of the refactoring solution is that they're going to move the update map view method from the bus monitor to the map monitor. The reason is simple. Because such a method involves a lot of methods in the map view. Therefore, move such a method will release the dependencies from the GUI module to concrete module. With the similar reasons, the refactoring navigators then suggest to move an update table view to table views. On the third step, it's going to suggest to move these 2 update methods and pull up them to an abstract view. The reason is also simple. Because make such a pull up, it can fill the gap of 2 missing dependencies. However, it is not intuitive from a human point of view. If we are a human developers, we are more inclined to move an updated curve view method to to curve view to make things more symmetry. Therefore, the developer can choose to reject these suggestions and ask the Refactoring Navigator to recommend again. With regard to the feedback, and the Refactoring Navigator then suggests that it should move the updated curve view to the curve view. On the fourth step, it will suggest move these two update methods to the object view. And finally, it is suggested to extract a new class so that it can fulfill these two missing dependencies. By this means, the refactoring is completed. Now, I'm going to summarize the examples with an approach overview. The first, we require the developers to specify their idea design, intended design into a target model. That is their target design. And afterwards, the Refactoring Navigator is going to extract the source code into a source model. Based on the target model and the source model, we are going to generate a reflection model which represents the difference between the source and the target. Based on the reflection model, we're going to recommend a reflection path which consists of a sequence of reflection steps. And the user can reject or accept the reflection steps, and their rejections and acceptance will be used in the user feedback. The accepted reflections will be applied automatically, and the remaining user feedback will be used to further improve the calculation or the recommendations. And in this approach, the most two important steps are the reflection model generations and the reflection path calculations. Let's start with the reflection model generations. Reflection model actually consists of three parts: a source model, a target model, and the mapping from the source model to target models. And in our FSC 2016 papers, we introduced an approach of how to match, and we encourage you to read the details. And after the mapping is finished, we are going to represent the difference from the source to the target in terms of three edges. The first is conformance, the second is a divergence, and the third is an absence. Conformance means that a module dependency is realized by a source module dependencies, and divergence means that an unexpected module dependency is realized by the source module. And the absence means that a module dependencies is failed to realize by the source module. Based on such reflection models, we're going to recommend a refactoring path. The reflection path calculations, the goal is to improve the conformance reflection model. That means we want to generate a reflection model with high conformance. It has as much conformance edge as possible and as little divergence and absence edge as possible. We do it with a search-based method. In order doing this, we are going to have three steps. The first is that we're going to define some basic reflection operations to transform the reflection models. And the second, we're going to quantify the conformance of reflection model. And third, we're going to find search algorithms which could use the feedback into consideration. And for the basic reflections, in our this work, we support three kinds of reflection operations. There are move method, pour field method, and extract class. And for the quantification of reflection model conformance, we're going to calculate the inconsistency of the reflection model. The inconsistency consists of an absence model, an absence age, and the divergence age. For an absence age in the reflection model, it will contribute 1 to the inconsistency. And for each divergence age in the module, we will also consider the set of correlation support such divergence. For example, given a module that module A should not depend on module B, but there is a divergence age there. Suppose the X class invokes Y 3 times and the Z class access field in Y 5 times. So such a divergence age contributes 3 plus 5 equals 8, contributing to the inconsistency. Apart from the inconsistency, and also consider lexical conformance in the design quality matrix. The major rationale is that we want to break a tie. When two reflection models have the same level of inconsistency, we will choose the one with better lexical conformance and the design quality matrix. Therefore, the final equations are like this. Afterwards, we're going to incorporate the user feedback. And now the user feedback, we allow the user to reject or accept refactions. So our rationale of incorporation that if a reflection is similar to reject reflection, they should get a penalty. And otherwise, it will get a reward. Therefore, these are basic fitness functions. We incorporate the user feedback in this way. If the reflection is similar to n accepted reflections and n reject the reflections, we're going to add the reward rate and the penalty rate to the original fitness functions. Okay, now we have basic reflection operations, and we have quantified a reflection model. So we search algorithms with search algorithms. We select the hill climbing algorithms for our search problems. Suppose that this is our current reflection model. We want to find a reflection model has higher fitness function. And in order to do this, we're going to attack all the basic reflection opportunities in the source model of the reflection model, so that we will detect a lot of reflection opportunities. We apply each reflection opportunities to the source model. Therefore, we will have a number of new reflection model, which is regarded as the numbers. And afterwards, we're going to choose the best numbers, and so we can move to the best numbers. By this means, we can quickly reach to a local optima. In our programs, we set a threshold for the number escape for a local optima. And when the number of escape is run out, we're going to reach a suboptimal reflection model. Therefore, the final reflection solution consisting the path from the original reflection model to the final suboptimal reflection model. We implement, okay.
Just a very clarification question. Is this escape, is it a new random solution, or how do you escape from the local optimum?
How do we escape? Because when we find a local optimal,
There is no neighbor that's better than.
Yes, yeah. But it may not. But actually, it is made of the local optimal. We may find another better optimal.
Yeah, I know, but how do you escape from the local optimal? Because there is no neighbor that's better than that one.
Yes, we can choose
a new random.
Yeah, technically, you can choose a sub-optimal, sub-best neighbors go there, and so we can escape it in the optimal. Okay. And based on our approach, we implemented an Eclipse plugin called Refactoring Navigators, and such a tool has a view which allows the user to draw their designs and to show the reflection model on such an editor. In addition, we listed all the recommended suggestions, that is the reflection path on the right. In order for the user to further check the details of reflection steps, we provide a detailed information view for user to check. We conduct evaluations with a controlled user study and industry case studies. And for the control experiment, we find a subject system which is written by an undergraduate student, and the scope is kind of realistic. It consists about over 1,000 lines of code, and it contains 15 classes structures, and also recruited 18 participants, and we divided them into two equivalent groups. And the experimental group which use the complete reflection navigators, and the control group, we use a partial reflection navigator, incomplete. That means they are allowed to use the reflection model, but they do not have the facility of recommendations. In addition, they also equipped it with Gedudorant plugin so that they can select the best mouse and apply the reflection automatically. And their task is going to reflection the subject system into a given design. This is our experiment result. And we find that all the participants in the finished reflection, so we evaluate the results in terms of completion time, the pass test case, and the line code added manually. We find that in completion time, both in completion time, it is shorter. That means with refactoring navigators, it is refactoring faster. And it passed more test cases. So the experiment group passed more test cases. It means it will preserve the program behavior better. Okay.
Sorry, I think I missed. Is it minutes?
It is minutes, yeah.
Minutes, okay.
Yeah. Yes, it passed more test cases. Means it can preserve the semantics program behavior better, and it means it's more safer. And in addition, it will edit much less line of code compared to control group. It means that it makes refactoring easier. In addition, we are going to conduct industry studies. We have cooperations with industry companies, and we help them to refactor their systems. We were going to use refactoring navigators to replicate part of the refactoring process. And the software systems have a lifespan of 8 years and consisting of 40,000 line codes. And the refactoring scope consists of 8 classes, which is less than 8,000 line code. And the main design problem lies in that it has a lot of Go classes, and the dependencies are quite entangling. And our results show that before the refactoring, and it will have, based on the refactoring models, it has 10 divergence dependencies, 11 absence dependencies, and after refactorings, almost all the inconsistent dependencies has been removed. However, there are 3 divergence dependencies cannot be removed. And we check the reason, we find that the main reason lies in that we only support 3 types of basic refactorings. And in some cases, our techniques kind of limited from an engineering point of view. So we may improve this part in the future. And finally, and I'm going to summarize the work, that is, if we want to conform the architecture refactorings, and the reflection model and the search-based techniques is very promising to solve the problem. And the second, we find incorporating the user feedback can prove more intuitive results. And finally, we're going to talk about the future work. We're going to, in order to make the tool more practical and have more usability, and we're going to support more types of basic refactoring. Oh, that's all. Thank you.